So, welcome everyone to the Arthur Holmes Medal Lecture by Jean Braun. You may be wondering who I am. My name is Jonathan Bamber, and I'm the past president of EGU, president until yesterday, actually. And the reason I'm here, and it's not someone else presenting or introducing Jean and doing the citation, is because the Arthur Holmes Medal is one of 4 union medals. And those, as I'm sure you know, we have 22 divisions within the union, and each of those divisions has its own medal award. But we also have 4 union medals that are cross-disciplinary, interdisciplinary, and across the whole union. And they are, if you like, the highest honor that we can bestow on a member of EGU. And so it really is a great honor to receive one of these 4. And I will just do the medal citation, and then there'll be some photographs, and then John will give his lecture, which I think you're going to enjoy and will be really fascinating. So Jean Braun is a world leader in integrated geodynamics and Earth surface process research. His research portfolio is unique in that he has a sustained record of high-impact and interdisciplinary research that transcends traditional boundaries in the solid Earth geosciences. For example, he has made transformative contributions to the fields of tectonics, geomorphology, thermochronology, and mathematical methods for geodynamic problems. And few, if any, has redefined the landscape of modern geoscience research in such a large breadth of fields. The success of Braun's research is rooted in a thorough evaluation of the physics associated with tectonic and landscape evolution processes. His research extends beyond groundbreaking theoretical work and includes world-renowned innovations in thermochronometer data interpretation and interdisciplinary high-impact contributions, which include publications on rift flank uplift, topographic development in orogens, the thermomechanical evolution of orogens, geomorphology, and dynamic topography. A characteristic and noteworthy aspect of his research is also his willingness to train young scientists on the application of his numerical models to geoscience problems. In this respect, his work in numerical modeling of thermochronometer data for tectonic and erosion studies has truly redefined how the next generation of tectonic students will conduct their work. It's difficult to find a study of the thermomechanical or topographic evolution of orogens that does not build upon previous work by Jean. His publications and book Quantitative Thermochronology occupy the must-read list of every new graduate student entering the field of tectonics and geodynamics. The interdisciplinary career accomplishments of Jean Braun make him, in our view, a worthy recipient of the 2019 EGU Arthur Holmes Medal and honorary membership. So, congratulations, Jean. Please come up to the stage. So just to let you know that tomorrow afternoon in this room will be the awards ceremony when Jean will actually get his medal and lecture. So do come along and share in the amazing achievements of Jean and all the other medalists and awardees tomorrow afternoon.
Many thanks, Jonathan, for these very kind words. It's a great pleasure for me today to give this lecture. And I want to first make reference to the amazing work of Arthur Holmes, who made significant contribution, as you all know, fundamental contributions to the solid Earth and the way we understand how it works. He was the first to propose that plate tectonics is likely to be driven by mantle convection, even at a time early in the past century when the theory of plate tectonics was not even accepted yet. He also spent a lot of time trying to establish an absolute scale of ages, both for dating rocks but also for dating events that scan the whole history of the Earth. It's interesting if we look at this second and maybe best known book about the age of the Earth, published in first edition published in 1913, that he also envisaged other ways by which we could date events in an absolute fashion. And one of them is to look at the accumulation of sediments in sedimentary basins, onshore and offshore mostly. And to do that, he also thought of maybe the most important thing is to estimate the rate at which sediments and rocks are eroded from the adjacent continents. And he undertook to do that. He published a few estimates of mean erosion rates for large catchment for a variety of rivers around the world, and noted that obviously the erosion rate, and therefore the rate of accumulation of sediments, is a strong function of what happens in the continent next by, and whether especially there is a large relief, a mountain belt nearby. As shown here with these high number for what we call now orogenic areas, and much lower number for what we would call now cratonic areas. He also used these very rare estimates they had of sediment flux coming out of these big river and river deltas to estimate a world average or continental average estimate of erosion rate. And he came up with this value of today's world mean erosion rate from continent of 35 meters per million year, which, if we compare it to our modern estimates based on a much broader and wider range of data sets that we have now, is actually very close. But I would like also to focus on that one sentence that I picked out of one of his books, that it is in the introduction of that chapter 4 on the work of denudation, in which he says, in the dynamical study of denudation and sedimentation, the first essential to know is the rate at which the rivers are working. And I'd like to follow Arthur Holmes' suggestion and take you and visit these rivers and how they actually interact with the solid earth to create this wonderful landscape on which we live, on which from which also we obtain most of the resources that we need to live. Now, mountain belts are the end product of uplift by tectonic processes and the corrosion of the surface that is so uplifted by a variety of processes, most of them involving water, flowing water, either in its liquid or in its solid form. For many years, tens of years, the study of the processes that are responsible for the formation of these wonderful landscapes was plagued by one limitation, and that limitation is the age that we can associate with a landscape. So the dating of rocks has been around for a long time, but it's not until the mid-1990s and the early 2000s that we came up with methods that allow us to date the time the rocks get very close to the surface as they are eroded away to form these landscapes. And we actually showed also that we can use the relationship between the various ages of the rocks at the surface of the Earth to actually say something about the age of the landform. So answer a question like, not how old is this rock or how old is this amount of sediment, but we can answer the question, how old is the shape of that valley? Has it been there for a few thousand years or a few million years? The other big revolution that took place about 20 years ago now in the field of geomorphology is the advent of numerical models. In the mid-1990s, it was fascinating to see how many landscape evolution models were published or created by a variety of groups all around the world. I had the chance to be part of that first wave of model developers. And when I say the chance, it's because working with landscape evolution models is actually a real pleasure. And why? Because the cost is relatively minimal, and the outcome or the pleasure you have in actually seeing what you're doing is actually great. And I'll show you this with a basic example of what most of these models that I briefly showed you that were created in the 1990s were solving. So we all solve, more or less, most of us, we solve a partial differential equation, which tells us that the rate of change of the surface topography is due to tectonic uplift, which can take a variety of form, both in space and time, the effect of rivers, which mostly in mountains erode, and we assume that the rate of erosion of a river is proportional to the amount of water that flows through the river, which will here take the drainage area upstream of a point in the river as a proxy for the discharge, assuming a uniform precipitation rate. And this erosion rate is proportional to drainage area and slope, the local slope in the river. And then we have these parameters which are poorly constrained, some powers, and then what we call the rate constant, which includes a lot of stuff which we don't really understand, like the effect of climate, the effect of lithology or fracturing, and many other things, or vegetation, for example. And then all of us added a second term, which we call the diffusion term, which represents the processes happening on the sides of a valley, the hill slope processes as we call them. And the most simple way to formulate that is to assume that the flux of sediments along the hill of a valley, or the side of a valley, are simply linearly proportional to slope. And you end up with a diffusion equation like this. And the amazing thing is that if you solve this on a regular mesh or by using all sorts of different numerical methods, you end up with, very rapidly, something that really looks like a landscape. And the reason is not magical. The reason is because we combine, in combining the fluvial processes or the river processes and hill slope processes, what we call long-range and short-range processes. The long-range processes connect different parts of the landscape by the erosion and deposition, sometimes, of sediments, and the short-range processes act against that to create or to smoothen the relief. And you end up, as shown in this very simple experiment, by having a landscape that is obviously characterized by valleys with interfluves. The different proportion, or between KD and KF, will tell us, for example, will control what we call the drainage density, the number of valleys you have per unit surface area. Now, one of the early targets of many of these models was to look at a classical form at the Earth's surface that had been studied for many tens, possibly in some cases over 100 years. It's the evolution of what we call a passive margin escarpment. And so when two continents rift apart, if they have some kind of a high elevation or even a normal elevation, what they leave behind is a step in topography. And remarkably, if we look at many escarpments that are still observable today at the surface of the Earth, for example, in southeastern Australia or in South Africa or in Southern America, these escarpments still exist. They haven't been totally eroded away, and they have moved away from the paleo coastline to an inland position, sometimes tens to up to 100 kilometers away from the original position. And yet, many of them have remains like sharp escarpments. And those models try to explain, seen under which conditions we can maintain an escarpment over such long periods of time. And one of the findings, which had been obviously proposed already by others, but that was kind of clearly illustrated by these models, is that to keep the escarpment as an escarpment, you need to make it a drainage divide. It needs to be a zone, a region where waters flow and diverge on either side of the divide. And to do that, the best way to do it is actually to imply in the model, indicate in the model, the isostasy. And isostasy works in this way in an escarpment. If you erode the base of the escarpment, it will cause an isostatic rebound, which pushes the escarpment up and makes it a drainage divide. I wrote a review of all this recently, and you can also show that the velocity at which the divide migrates backward is a proportion, governed by the proportion between the width of the escarpment and the thickness of the underlying elastic lithosphere. But there are many other aspects of numerical modeling in geomorphology that led to what I call more an inspiration. That is, models not only try to reproduce what had been proposed before or reproduce landscape, but they also provide these fresh ideas. An example, although it had been proposed and suggested as a potential way in which landscapes could behave is this idea of a steady state landform. And if you impose an uplift to one of these models and let it run for long enough, it will actually get to a steady state here where the form doesn't change. The valley stays more or less where they are. The height of the mountains or the relief stays the same. But uniformly and through time, rock are still uplifting and eroded away and potentially deposited in an adjacent basin, even though the surface is not changing in its shape. But there are many other concepts that were introduced or quantified by numerical, through the use of numerical model. For example, the velocity at which Nick points propagates upriver networks in response, for example, to a base level drop, the concavity of river profiles, the self-similarity of various landforms and how they can be achieved, how a mountain or a landscape responds to a variation in climate or in tectonic forcing, and then many, many others that I don't want to take the time to describe today. Maybe more importantly is by using numerical model of landscape evolution to connect the climate to the underlying tectonics, like was done early in the 1990s. The use of this numerical model really opened up almost an entire new field in tectonics, and that's the study of the interactions between climate, rainfall mostly, and tectonics. And the idea is that as you create a mountain belt, due to maybe the subductions of a continent under another, or following the end of a subduction of an oceanic basin, closing an ocean basin, the mountain that you create by leading to the formation of topography will affect the way rainfall distributed at the surface of the earth and will enhance the precipitation on one side of the origin. And that will enhance the erosion processes on that one side of the origin, and therefore may lead to a very highly asymmetrical tectonic response, having this window of exhumation preferentially on one side of the mountain than the other. And you can show, these were models, that they showed that by changing the directions in which the dominant wind directions, the wind come over the origin, you can actually flip what we call the metamorphic polarity of the origin, having the highest metamorphic grade rocks being exhumed either at the base of the model, at the base of the mountain, or if we flip the erosion and make it more efficient here, the highest grade rocks will actually be exhumed near the divide. These were concepts that are hard to prove from the geological record, but they led to a flurry of new attempts to prove that, and as I said, almost a new field in the study of the interaction between climate and tectonics. Very worthy to notice is another paper too that showed how all the previous concepts that had been introduced sometimes over 100 years ago by a famous geomorphologist and could actually be reconciled by considering these very simple models and considering that the various styles of landscapes and how they evolve through time has been proposed by these great geomorphologists would correspond to simply different type of forcing, whether the uplift is continuous or very abrupt, or whether you have various types of climate under which the landscapes and the mountain belts develop. But what I want to do today, and spend most of the time on my presentation, is to show you how models continue to inspire us in the work that we do today. And I'm going to use some of the work that I've been doing over the last 5 years that I continue to do now with a lot of postdocs and PhD students at the GFZ, and try to relate them also mostly to what's happening inside the solid Earth, and not focus too much on what's happening in the atmosphere in view of the audience that I have here today. So I want to focus, and I hope I'll be able to go through all these points. I have a timer, so I'll try to stay on time. I will try to show you that there's another source of topography that is not driven by tectonics, but driven directly by mantle flow. And I'll try to see if we can see or have evidence that this topography is also affected by surface processes and how it can actually help us to provide evidence that the dynamic topography existed from the geological record. Big questions nowadays in geomorphology has kind of gone back to the stability of drainage divides in continental interiors, and I'll mention some work that we've been doing in this. And then the very new and exciting new development that we are working on, and many others, that is to actually try now to see how much the biota, especially vegetation, but also other form of life, may actually influence Earth surface and evolution, and vice versa. We've also put a lot of emphasis on what happens in mountain, and I want to show you a little bit that we have forgotten all these cratonic interiors, and that much attention should be paid to them. And finally, if I have the time, I'll mention the importance of considering the climate, and especially the climate variability, to understand how efficient the erosion is in a variety of settings. Dynamic topography is the topography created by the flow of material in the convecting mantle. Where low density material exists, it goes up, and as that flow is forced to diverge as it gets close to the surface of the mantle, the divergence of that flow causes a stress at the base of the lithosphere which uplifts it. Similarly, when cold material goes down, it creates a subsidence of the surface. That topography is of a relatively low amplitude, a few hundred meters to maybe a kilometer, and a very long wavelength, a minimum of 1,000 to up to 10,000 kilometers. It's to be differentiated from what we call isostatic topography, which is related to variation in crustal thickness, especially continental crustal thickness, which leads to mountain belts and sedimentary basins. Now, one of the key questions is that dynamic topography really of finite size, and can we document it in the Earth history? The only way we can hope that it leaves a mark in the Earth's history or in the geological record is that it actually be eroded. Either we can measure directly its erosion using thermochronological method, or we can look at the product of the erosion in sedimentary basins. The key here is that the models that predict mantle flow and dynamic topography rely on the knowledge of mantle viscosity and the distribution of density inside the mantle, things that we don't know very well and we don't know how to scale very well. So one of the purposes of doing these, or of investigating whether there is a geological record of dynamic topography, is to provide constraints and feedbacks to the modelers, the geodynamicists to study mantle dynamics, and give them constraints that they can use to calibrate their models. I'll take an example from Southern Africa. Southern Africa has a very anomalous topography. It sits about 1,000 to 1,500 meters too high compared to a normal continent. And the reason it's sitting up there, it's supposed to be, or most likely in relation to dynamic topography, and most importantly, the one that is actually created by what is the so-called African superplume. This is this highly anomalous hot or a material that sits at the core mantle boundary, and it potentially creates a very large dynamic topography, both in amplitude and in size. Interestingly, if we look at the geological record around in the basins around the South African plateau, we see that in all the basins that surround the plateau, there are two major phases of sedimentation. One corresponds to the rifting of the various continents around Africa, and more likely the erosions of the margins, the retreat of the escarpments I talked about previously. And then this very anomalous but enormous period of sedimentation that took place in the late Cretaceous, and for which there is no tectonic justification. Africa was away from any active plate boundary. There was no mountain building. Yet, we have this really massive phase of erosion and deposition in the basins, followed by a period of total quiescence. And in 2014, with my co-author, we proposed that this phase corresponded to the time in which Africa climbed over the superswell, was slightly tilted during that episode, and caused a massive erosion of the continent and the erosion of what I call the Karoo sediments, which were deposited before rifting took place. And then as Africa stabilized over the super plume, it became flat again, and that what is mostly was responsible for the end of this depositional or erosional depositional phase. What I want to show you now is how we can use models to test these ideas in a very quantitative way, trying to integrate a variety of geological observations into the models to get insight on the tectonic uplift, the history of tectonic uplift of the South African plateau, and more importantly, put constraint, uncertainty on the estimates we get for this tectonic uplift history. And to do that, I'm proposed to use, and we've been doing this now for some years, what I call a Bayesian approach to use the use of numerical model. And I'm going to show you very briefly in one slide how it actually works, and then I'll show you how we have applied it to South Africa. Here I've taken a fake landscape, and I'm going to ask the question, I know here I've used that equation to produce that landscape. And I know that I've used a given uplift rate, which is uniform here. I've used a value of that parameter, which don't really know, and another value for that parameter. And what I'm going to do is going to ask now, just by knowing the shape of the landscape and maybe some other fake data that I've produced, can my model recover these numbers, these parameter values that I've put in the model? And obviously, I'll be most interested in trying to recover the uplift rate just by trial and error. And to do that, I'm going to define what I call a misfit function, which is a way to measure the prediction of my model and compare it to the data. And then I'm going to use this model and run it many, many, many times. And every time I'm going to run the model, I'm going to predict a landscape. I'm going to compare it to my target landscape, and then take a decision on what to do. And what we do at the beginning, we're going to produce many models at random. This is parameter space, so this is the value of U, and the value of KF, and the value of KD. Each dot corresponds to one attempt to reproduce the model, the landscape. So it's one value of these three parameters. And we see at first that the model is searching, this method is searching kind of randomly, but by using a clever optimization method, so-called the neighborhood algorithm developed by Malcolm Sandwich, we can actually focus the search in area where the misfit is minimum. And very rapidly, you see that the method will actually converge, and in this case, will recover very nicely the value of the parameter KF and the value of the uplift rate that I've put in this model. What it cannot recover here is the value of KD. And this will happen all the time. Okay? There are parameters for which we don't have data that actually is relevant to the value of that parameter. But what we can see, even though we have not really been able to recover the value of KD, we still have very accurate value of the important parameter here, which is U. So let's apply this now to South Africa. This is the data we have. This is the flux of sediment that's coming off all the margins of Southern Africa in these various basins through geological time. We also have estimates of the rate of erosion of the plateau at various places on the plateau and at various periods in the past. That's using thermochronology, using mostly apatite efficient tract and apatite helium data. And then, of course, what we want to reproduce is the topography of South Africa. Obviously, we don't want to reproduce the details of the topography, but its general characteristics, like the distribution of height, the distribution of slope, and or curvature. And so we've run about 100,000 of these models. This is something we also do in my group. We try to make this model by developing new numerical methods, highly efficient. So to actually model the whole evolution of Southern Africa in about 100 and here in this case 44 million years, takes about 2 or 3 minutes on a computer. So that's why we can run so many of these models. And I'm going to show you the best fitting model. And while the model is playing, I'm going to show you what actually we can derive from this inversion. First, we derive from this inversion and from the data we have available that the initial topography of the plateau must have been relatively low, only a few hundred meters. Most likely is that the eastern margin uplifted first about 100 million years ago in the late Cretaceous, and then soon after, the western margin follows suit. The total uplift at that time was quite large, of the order of about 1,000 meters. Best models that we obtain, the best fit to the models, that the observation that we get, also need a renewed uplift at about 30 million years ago, but of a much lesser amplitude. And so when we see now this relatively short time of equilibration, if you want, of uplift on one side and then the other, maybe the motion of Africa over the superplume is maybe too slow for this, and maybe we have to consider other processes like lithospheric delamination, as was recently proposed by Hu et al. In 2018. What's also very interesting is that in order to reconcile the amount of erosion we measure on the continent due from the thermochronological data and the volume deposited offshore, we kind of lose about 50% of the volume of sediment. And one of the possibilities to actually account for that is to say that this Karoo sediment and all the large amount of basalts that were intermingled with these sediments were actually removed not by physical erosion but by chemical erosion. I'll briefly go through another example of that method, which is now applied to the southeastern Tibetan plateau. So you see I'm trying to stay close to the solid earth interest here. And big question we ask about that part of the world is whether, at what time did the southeasternmost part of the plateau uplift it, either by simple uplift or maybe by crustal thickening or by propagation of a channel flow in the lower crust beneath the plateau. And the other question that's relevant for this part of the world, which is more important for those interested in paleoclimate, is whether the uplift of the plateau led to an intensification or, as some suggested, a diminution of the intensity of the monsoon there. And for that, we'll use what we now all call a source-to-seeing approach, where we try to reproduce the detail of what we see in the offshore record to say something about what has actually happened on the continent, in that case, in the Tibetan plateau. And for that, the data we have is a series of seismic cross-section from the South China Sea, the basin here in the South China Sea, an example here. And we're not going to only trying to reproduce the volume of sediment deposited, but also the position of the shelf break here and the slope of the slope here through time. And we can do that because we have also developed a model for sedimentation in the marine environment, which I can't present to you due to the lack of time. Other data that we have our observation is the shape or the profile of the Pearl River, the main river that drains the Tibetan plateau today, and its evolution through time, on which we have some constraint due to this very nice study by Cao et al. Based on provenance study in the area and sediment recovered here in wells in the South China Sea. So I won't show you a nice model, or I will show you here another way we have to present the result of this Bayesian inversion. Is for a few of the parameters that we have free parameters in the model, we don't say when the plateau started to uplift, we don't say by how much it uplifted or the rate at which it uplifted. We don't give the value of the erosion parameters because we don't know them. All this is left as free parameter. And we try this inversion. In this case, the inversion converges very nicely. And after only a few, let's say 10,000 models, we start to see all the parameters values to converge. And I'm going to show you here only 4 of these inverted model parameters that are significant for the questions I asked earlier. We see that the model, most of them converge to this time of start of uplift of southeastern Tibet of about 14 million years, which is in agreement with many other studies based on other observation. We also see that the Tibetan plateau grew at that time, that there was not many topography, at least in southeastern Tibet. I'm not talking about the central part of the plateau here, but it was a relatively low-lying continental area prior to that. And maybe more interestingly is that whatever we do with the model, they all seem to converge to predict a decrease in the erosion efficiency of the system after the uplift of the plateau, therefore suggesting that the monsoon didn't then intensify, but rather decrease in its intensity, or that maybe the frequency of large monsoonal rainfall events decreased, and as I will show you, because this has a bearing on the efficiency of rivers to erode bedrock. Now, a very brief aside on the study that we have done with, I must mention that the leader of this study here is Xiaoping Yuan, who has a presentation on Thursday, and if you want to see more detail on this, please go and see his presentation. Now, this is the work that I've done with Jia Ruong on the geometry of drainage, continental drainage patterns in a global sense. And you can summarize the question that we ask ourselves with these very basic questions. Why don't rivers flow straight to the ocean? If you look at the major rivers of the world, like the Mississippi, the Congo, the Darling River, the Murray-Darling River in Australia, they don't go simply straight to the ocean. They tend to form these very dendritic patterns and collect a very large drainage area, and then they connect to the ocean through this one exit point. For example, the orange mouth here for the Orange River in southern Africa. And why is it important to consider that? Because we know from many other studies that the way the fresh water that flows on, that rains on the continent is delivered to the ocean at what latitude, on what side of the continents, strongly influence the distribution of salinity in the oceans and therefore the global circulation of the oceans and thus the climate. Also, we know that the size of these large continental or drainage basin has a strong control on biodiversity. And our hypothesis comes back to what I showed you earlier about escarpment and retreat, is that most continents are actually characterized by a topographic high or a moat that was formed during the rifting that led to the formation of the passive margin. And to show that to you, I'll show you again this animation here. And you can show in the back here that all the rivers seems to collect in a low topographic low here, a small, topographic low that forms behind the escarpment. And we call this an axial river that collects the water that flows off the escarpment, but ultimately, if there was a continent here, it would collect the rivers that flow and try to reach the ocean. And the position of that axial river is actually determined by the flexural wavelength of the lithosphere, which itself is related to the thickness of the lithosphere. We can also show that, if you deposit a lot of sediment offshore here, the axial river can be shifted back a little bit. And so we expect this axial river to be located anywhere between 1 flexural wavelength and 2 flexural wavelengths from the edge of the continent. This is an example of a few models we run now at the continental scale. They're just here for illustration purpose. And you see that if we have a very weak continent with a very low flexural wavelength, all rivers tend to flow to the ocean, and we don't form axial rivers. In the case of a normal elastic plate thickness for a continent, we see that we form these axial rivers, which collect most of the drainage pattern, and then that's from that axial river that a single channel will flow to the ocean. And in case of a very thick, we can actually, lithosphere, we can have actually more than one axial river as the distance gets really too large. As the flexural wavelength increases, the height of the deflection that it creates goes down. So to prove our point, we've actually run, again, a very large number of models, taking the various parameters of the models, both the flexural thickness, but also all the erosion parameters at random within acceptable range. And we've produced this relationship between the effective elastic plate thickness, which sets the width of the flexural wavelength, and the distance of axial rivers that we predict in the model for all this range. And we see that most of the model here, these are all the models, this is a density plot of the same models, sit between these two lines that corresponds to what we'd expect, if it was at 1 flexural wavelength away or 2 flexural wavelengths away. And then we superimpose on that the location of axial rivers for a large number of big rivers on continents. And obviously, we excluded those rivers that flow off active plate boundaries. These here are those where the continental ocean boundary is very far from the edge of the continent, and therefore these margins are mostly more likely to be affected by sedimentation than these. And you see that the fit is reasonably good, showing that there is, in our opinion, a first-order control on the patterns of continental drainage from the underlying thickness of the lithosphere. Now, there's a lot of work in recent time that has been devoted to the influence of life on landscape evolution. For example, whether vegetation really helps, or different types of vegetation helps, or contrary, dampen the effect of erosion, especially by rivers or other processes. What I want to take you through now is the potential feedback that may also exist, and the way the evolution of landform may actually bear on the evolution of life and the diversity of life at the Earth's surface. And this has been inspired by a very simple observation. If you look at the population or the many different species of lemur that live on the island of Madagascar, others not me, I've actually looked at the genome of all these different species and the way they connect to each other through their ancestry. And what you find by constructing these phylogenomic trees, or phylogenetic trees as they are called, is that the major events of speciation do align on a geological time scale, on the time scales of tens of millions of years. And for example, this here corresponds to what we estimate to be the main event of uplift in Madagascar that created the main divide in the middle of the island. That's where you split the population that live on one side of the island or the other. So what we've done now is actually seen in ways in which we can take topography and some estimate of precipitation, or real precipitation in this case, to predict, using some clustering algorithm, the distribution of habitat at the shape of the surface of Madagascar, and how this actually compares to real habitats for these lemur. And we see that the fit is reasonable. We can predict, that the habitats here are elongated and very narrow on one side of the island, whereas on the other side they are much broader and cover a wider range of elevation. So what we've done is try to implement that in our landscape evolution models to see if we can predict the evolution of life on such a landscape. And for that, we use the work of others who've basically said that if we assume that at a given position on the landscape, there is what we call a trait, that is a measure of how well, if an animal or a plant has that trait, it will fit on the landscape. And that trait for us is going to be some kind of a convolution or derived from elevation and precipitation. We can actually produce a fitness that each member here of our population will have. We also add a component to that fitness, which is related to the density of the population. This is called competition. And then if the specimen here or a couple is actually fit, it will be able to reproduce and generate offsprings. And the offsprings will actually mutate through time to slightly change their trait, and they will also be allowed to migrate on the landscape. And by doing that, we can therefore predict how a population is going to evolve on our landscape through geological time. And you see only one half of the landscape here is uplifting, so that we preserve a lowland species, which rapidly becomes disconnected from another species of range of species that live in the highlands. Here, it's for each individual on this landscape, we have the trait, so that's his own trait, and I plot here is optimal trait, which is set by the range of elevation and rainfall that it actually feels, in which it lives. Okay? And you can see that even if we let the model evolve sufficiently long, we're going to create a highland, a middle elevation, and a lowland population. And from these, we can actually generate synthetic genomic trees like these. And I strongly suggest you go and talk to Kat, who is here in the audience, but she has a poster, I think it's tomorrow morning, where she will give you all the detail of this and analyze these results in much more detail than I can do it now. But we can show that on a static landscape, the ultimate diversity or biodiversity is much less than on an uplifting landscape. And we can also show that obviously the time at which the onset of uplift will dictate also the onset of speciation. I want to say a few words, as I see the time is going by, about these left-over regions of the surface of the Earth. Now, we focus mostly on mountains and mountain areas, but about 70% of the Earth's surface is flat. And in these areas, we haven't spent much time, especially us in the modeling community, to try to come up with ways of parameterizing the evolution of these surfaces. And one type of surfaces, which is really strange and difficult to explain, is the pediment, which covers many parts of Africa, Australia, or South America, these quiet cratonic areas. And the pediment is a strange surface because it's a very low slope area that extends over sometimes hundreds of kilometers, but it is an erosional surface. It's not a depositional surface. So we don't really understand the process by which they are formed. We believe it has to do with weathering and the removal of a weathering or regolith layer, but we don't really know. Only few models exist that can reproduce these. What I'd like to focus on today is things that we have been actually working on now, especially with the group of François Guillochot, but also colleagues in the University of Le Mans, and trying to identify in a most objective way these surfaces and maybe generation of surfaces that may be created by various episodes in base level fall some position on the landscape, usually on the edge of that landscape. And to do that, I'm using here an example from the Massif Central area in France, where we've used a DEM that was provided to us by Paul in Le Mans, Paul Bessin in Le Mans, and asked the question, can we actually identify in this area if there are distinct surfaces? And to do that, all we give, and this is again the work of Katrin Kravich here, and please ask her if she's done it in the detail if you want to know more, but at every point of that landscape from the EDEM, we simply calculate a local slope, a local height, of course, and some kind of an estimate of a roughness. And then we give to these clustering algorithm simply that information. We say, can you find families or parts of the landscape that you have the same properties, but we don't specify what same means or even if it has to use all the properties to do so. And if we say, try to find two families, it finds two surfaces. If we say three families, it will find three surfaces. But then if we say, try to find more by families, it will actually converge to define these three surfaces. And we can be confident that these surfaces share some properties, but it's not us who have told this method what should be these properties. And therefore, we think it's a more objective way to find these surfaces and analyze them. And this is an example that I want to show you now how they can be used potentially as markers of uplift by going back to Madagascar. This is the work of Antoine Delaunay, who finished his PhD thesis in Rennes a year ago or so, who has mapped, with the help of many in Rennes, various surfaces that had identified mostly from field work, but also from DM analysis. And they have a whole generation of these surfaces. Now, the hard thing is to actually say the age of these surfaces, or the age at which they were formed. Or if they do correspond to various phases of uplift, but by how much have they been uplifted with respect to each other. So what we can do is use our Bayesian approach to say, okay, we want to produce these surfaces in some way, but we don't know when the uplift was, and we don't know how much the uplift was to create the various surfaces. We have additional information, though. We have flux of sediment coming out of this part of Madagascar. So it's not very good information, but we have evidence that there is sediment through the geological time that goes through here, and we know how much roughly. And so we can use this Bayesian approach again to invert both the surfaces, but we leave the time of uplift and the amount of uplift of each surface as a free parameter. And this is what we come up with. We come up with a major event in Madagascar, which is basically related to the rifting of Madagascar. But more importantly, we come up with a series of uplift events starting about 40 or 30 million years ago. I can play the best fitting model, which doesn't mean really much here because we haven't taken into account variations in sea level, but really it shows you that we can reproduce somehow, and we're still working on this, the evolution of Madagascar through time. Rather than this fancy movie, the important thing is that we can invert all this information into a relatively well-constrained uplift history. Now, last thing I want to talk about, and I think it's very important because it really leads us to a new area for these models of landscape evolution, and one that maybe is most relevant if you want to study the near future evolution of landscape evolution, potentially those related to the anthropogenic effect on the Earth system. If we go and sit next to a river and look at a boulder like this one, you can sit there for hours. That boulder is not going to move. You can go back the next day, it'll still be there. You can go back every day for a month or for a year, it'll still be there. And then one day, there'll be a big storm, or if you're in Southeast Asia, there might be a hurricane coming by. You won't see anything because the river will go up, the level of the river will go up by a couple of meters, but when the river recesses down, you come there and the boulder is gone. What it means that in many Earth processes, or surface processes, there are thresholds. That in this case, the level of the river, the discharge in the river has to reach a threshold level to actually cause any work that will cause erosion or transport of material. And so the question that becomes very important is to assess the variability, the effect of the variability, for example, here of the flow of the river on a daily basis, and assess how this actually affects the erosional efficiency. So now you've seen that our models runs over tens of millions of years. So I certainly don't want to run my model on a daily basis and try to guess the rainfall pattern and the discharge pattern in Madagascar over the last 80 million years. Okay? So we have to have another approach to that, and that approach is statistical. So what we do is we actually look at constructing from real data or from other models the distribution, not a time series now, but a statistical representation of the variability of flow in the river, which takes the form of a probability density function of a given relative magnitude of a discharge event in the river, daily event. And you can characterize it by a curve that has this shape, and different rivers, which are eroded under different climate, will have different of these characteristic curves. And what's really important for the erosion efficiency is how often that curve, so the area under that curve, that is to the right of an assumed threshold. And you can see that if the threshold is very high, if the distribution shows low variability, there are not many events of very high magnitude. There are many more events of low magnitude or mean magnitude. then erosion efficiency will be very low. On the other hand, if the variability in the river is really high for that value of the threshold, there will be many events that actually cross the threshold and the erosion efficiency will be much higher. And therefore, you can come to this conclusion that the mean discharge might not matter that much, but it's the variability that matters more than the mean discharge. You can also show it here where you see that, in this case, with a low variability discharge variation, discharge distribution, you have to come back to your river every 10 years to see something change. Whereas you can actually come back every year or less, or every month, and you will see something happening in the river. Now, the whole question whether variability matters or not, obviously, is where the threshold sits. Because if I have a very low threshold, in this case, you'll have actually potentially even more erosion in this case, because all events will actually produce erosion than in this situation. So this is the work of a former PhD student of mine, Eric Deal, and please go and see his PhD if you want all the detail of this. But Eric has shown that what really matters, whether, to decide whether thresholds are important or not, is where the threshold sits compared to the mean value of the forcing. In this case, where the threshold discharge sits compared to the mean discharge. And if the threshold is higher than the mean, that variability matters a lot. If the threshold is lower than the mean, variability doesn't matter. And this is shown here in this plot. What we've done is, again, run millions of models, okay? And we've invented processes. We've said that erosion rate, once you're beyond the threshold, can increase more than linearly with discharge, or increase less than linearly with discharge, or can even sometimes decrease with discharge. If you, for example, there's more and more sediment coming in the river, and in the roads, it makes the river deposit more than eroding. And in all cases, what happened here, these plots are efficiency of erosion, so time-integrated erosion, as a function of where the threshold sits versus the mean. And we see that for all the values that are below 1, variability doesn't matter. But if the threshold, if the threshold is way over the mean, variability does matter. And you can have variations in efficiency of erosions by orders of magnitude for the same mean discharge, depending on the variability. So the key for us now is to determine what is the threshold and what are the thresholds for a variety of processes. And this is, if you want to know more about this and how actually you can predict discharge variability from rainfall variability, you should see the poster of Igor, who is on Thursday, I believe. Yes. But to actually try to assess whether these thresholds exist, we can go back in the field and look at some cases. For example, here, this is the work of Kim Herpert. She's here. You can talk to her. She won't present this work here at the EGU, but you can definitely talk to her to get more insight about what she's done. But she's been working on the island of Kauai, in the Hawaii, and she's looked at this very interesting system where Hawaii or Kauai experiences a range, an enormous range in mean precipitation, but also in the variability in precipitation. And the good thing is in Hawaii, we have good data on rainfall, but we have also very good data on river discharge. And because we can estimate the amount of incision that a river does, since a lava flow was erupted at the surface of Kauai, we can date the lava flow, so we can actually have an estimate of the total erosion that since that time to the present day. And so we have a control on erosion, the product that we're trying to predict, and we have a control on the forcing, the rainfall and the discharge in the river. It's a bit complicated because Kim, the estimate we have of erosion is over 5 million years. So Kim had to actually kind of backtrack for 5 million years the rainfall pattern of Hawaii, which we know are strongly influenced by the presence of El Nino events. And as we know, the frequency of El Nino events changed through time. We kind of adjusted the rainfall and the discharge observation for that effect. Problem is, and I won't show you Kim's conclusion, because her conclusion so far, and I'm pushing her in the back to say, we have to search more because I don't like the conclusion, Kim, is that thresholds don't matter. In Hawaii, apparently, thresholds are very low, and therefore variability should not matter very much, which is a result. Okay, of course, maybe not exciting as it had been the other way around, but it's a result in itself. So I want to leave a few minutes if you guys have questions, so I will go to my final slide, which is maybe seeing where the future takes us. And I I'm going obviously to focus on modeling and modeling Earth surface processes, but I think what I'm going to say applies to many of us who are involved in trying to reproduce the geological record in various ways through models, but also to try to extract from it as much information as we can. I've shown you that so far, all the models that I've shown you are based on relatively simple upscaling of observations that have been done at the bottom of a river or in a flume, and they've led to the stream power law or simple expression for hill slope processes. Clearly, we need to improve that representation of the processes, and we have already done that. With Frederick Herman, we've worked a lot on glacial erosion. With George Kaufman, we worked on the formation of karst. Many, for example, in Rennes, are working on the importance of landsliding and how they relate to various forcing. I mentioned marine transport is something that we also work a lot on, and it's a very complex problem. But all of this now, because we want to integrate that into these processes, especially, for example, in landsliding, the variability of the forcing, we need to introduce more the statistical approach I mentioned. We also need to develop algorithms that will remain efficient or even become more efficient so that we can still use this Bayesian approach. And I really like the Bayesian approach, which I think are really suitable for what we're trying to do because we have a very large variety of data. We have super high resolution DEMs, but they only give us the snapshot of what's happening at the end. If we look back at time, in some cases with a very high resolution, temporal resolution of a process, but only at one location somewhere in the sedimentary basin. And sometimes we have good spatial coverage, but very poor temporal coverage. And I think building what I call this misfit function becomes like a skill, but it also allows us to bring this variety of data. Now, since I moved to the GFZ, I've also noticed that there are people who now collecting enormous amount of data, new data. Of course, DMs, LiDAR. Now, I think there's a project to know the surface of the Earth at a resolution of a meter or even less, a centimeter in the coming years or decades. So we wouldn't going to have a super high resolution, accurate measure of the surface of the Earth. And we can do this repeatedly in time. Now we're starting to build databases of the surface of the Earth a year ago, 10 years ago. So we can extract from that evidence of the evolution of the Earth, but on our time scales. We have also very high resolution climate data that's coming up. And therefore, we have to invent new methods to actually involve these in redefining the processes and getting into more the detail of the process. But we also need new methods to actually include these data and make them fit into this new representation, and ultimately also in these integrating methods to combine. And therefore, I think this is really where the challenge is going to sit now, is how we're going to integrate these large data sets into our model in a clever way. We'll never be able to reproduce the surface of the Earth at a millimeter scale over the next 100 years, but we can use the information that we have gathered. So I think this is exciting, and as you know, I now lead this group, this new section at the GFZ in Potsdam, and I welcome any young geomorphologist or solid earth scientist who wants to join us to come and contact me during the rest of the week. Thank you very much for your attention.
Okay. I think that we were all so impressed by John's talk and the inspiring messages he brought to us today. I'm Mioara Mandea, and I have with you 1.5 minutes, just time to see if there are any important questions. We have time to take one or two. And you have to use the mic. Yes, please.
So the question is regarding the when you solve the inverse, well, the forward simulation with the different parameters of uplift and decay. Then you start from an initial condition, and then can you hear me? And then you assume you have a final solution which the Bayesian approach is going to tell you sort of what is the final solution, but you have no way to know if the in-between steps are known or not. And you're assuming as well that the uplift rate is always applying, so it's constant true time. Have you taken into account or find a way to look at an uplift rate that varies through time, or that it actually stops through time as well?
Yes, of course, and as I showed in the example from Madagascar, we assume a series of uplift events, but we don't know when they take place, and we don't know how much each event is in amplitude, and we invert for that. But we can also have a spatially variable uplift rate, like we did for South Africa, allowing for a tilt of the continent or not. This type of approach, Bayesian approach, the method we use limits us to a finite small number of parameters we can invert for, about 20, to give you a number. We have to use other methods if we want to invert for a larger number of parameters that we don't know.
Okay, I think really we are out of our time because the session will come back here after. So once again, thanks again to Jean. And for sure, he will be around all the week, and if you have some other questions, please address to him directly.